finish this guy up, how would I do that? This will be 1/2 x squared, ln x minus, be 1/2 integral x dx, of course. And then what's that? What's the integral of x?
Minus 1/2. Well,
Yeah,
one.
it'd be 1/2
One.
x squared, so 1/2 is 1/4. Plus c. Now real quick, in general, what else would I have to tell you so you can figure out what the c is? Yeah, I have to give you, it could be called boundary conditions. I just have to give you some output for an input. So, and why is that true? What is integrating something actually, well, all right, let me say it like this. If I know the derivative of a function is this, and this is going to be really basic stuff, but that's okay. Okay. What does that tell me? The derivative being x ln x. What does that give me access to figuring out if I plug stuff in? Slope at every point, correct? And of course, this guy does not have a slope defined everywhere, correct? Where's the slope defined? So bring with me that from integrating x natural of x, I'm kind of assuming there's a function whose derivative is x ln x, correct? So if I plug stuff in for x, I figure out what the slope is. Just because I know the slope does not mean I know where the hell the function is. So I mean, how many lines have a slope of 5? Infinite number of them. So just because I know how it's moving doesn't tell me where it is. It sounds very, anyway, I won't go there. So of course, to figure out what the plus c is, I just have to have one place where the function exists, and then from there its slope kind of draws the rest of it. I know I'm making a big deal out of something very basic, but that's going to be a huge part of this class is, since our equations deal with relationships between slopes and higher level derivatives, we can actually analyze the equation by itself before we try to solve it and just see what does it tell me directly. So the equation dy dx equals 2. That's a differential equation. Silly basic one, right? That just tells me the slope of the answer is everywhere 2. So of course we know the answer is in line. We just don't know, so we know it's 2x plus c, we just don't know where the line is. Okay, okay. All right. Did anyone make it to part C? Either in class or later? Or did you guys just leave and not look at this ever again? Like, no, screw this thing. Is this a trig sub? Why not?
No squared.
Yeah, it's no squares, right? So, I mean, part of your brain might say, maybe it could be a trig sub, just really gross. So let's not go there. It would be really. Did anyone try anything with this? All right. U sub. Yes?
The fancy U sub, and then you make.
Ooh, the fancy U sub.
Yeah.
Why do you call it fancy U sub?
Jenny called it that when she showed it to us.
Who did? Oh, Jenny?
Yeah.
Okay. I'm not going to try to compete with Jenny. So she's the one who stole the ultraviolet voodoo from. But, yeah, so one reason she might have called it fancy is because, for example, what would you let U equal here?
X minus 1.
Yeah, x minus 1. And the funny thing is, a lot of professors, when they teach U sub, they only teach basic U sub, which really sucks. If U is x minus 1, then x, of course, is U plus 1. Now, very quickly, I really want this to make sense. If this problem had instead been, I say that a lot, if this problem had instead been this, why is that easy as shit? I'll say that a lot too, and if it's not easy, I'm sorry, I apologize. Yeah.
Distribute the square.
Yeah, it's a stupid x to the 1/2 distribute. It's just a power rule, right? You know, yay. So what sucks about the problem I gave you is that the inside of the radical is not a single term. So the way to look at this fancy U sub is, okay, let's force the inside to be a single term. Because I want it to be, damn it. And so if, like I said, U is x minus 1, what is x? U plus 1. The really cool thing about doing this is you can figure out what dx is directly, even though this is stupid easy either way. But dx is du, yes? Alright. Now here's where I'll be a little more careful than normal. Let's go ahead and change the limits. Those of you who took Calc 3, you know the full extent of how evil changing the limits of integration can get. Because then you're talking about whole regions and trying to figure out, scan this way, now I'm going to scan it that way. Oh my God. That's always exciting. Normally when I teach Calc 1, especially recently, I've been careful about actually changing limits, but when I took Calc 1, I never changed the limits. I would just put 1 and 2 in parentheses to remind me that that's not what U is doing, that's what X is doing. And then I would just bring X back. But it's a good idea to change the limits in general. So, what do the limits become?
0 and 1.
Do it again, sorry.
0 and 1.
0 and 1. And then X is U plus 1. And then square root of X minus 1 becomes U to the 1/2. All right, and now we can do what we wanted to be able to do, right? I kind of like this. This is us taking the problem saying, I don't like the way you look, and then you switch it. By the way I teach math very rarely is life lessons. Just math lessons, right? Don't take somebody, I don't like to look at you. So what does this become now? This is just going to be U to the 3/2, thanks everybody, U to the 1/2, from 0 to 1. Yeah. So then you get, integrate that, what do you get? Anybody? Yeah, it'll be 5/2, so in front will be 2/5. This will be 3/2, so in front will be 2/3, and I'll be going from 0 to 1. 0 is beautiful here. 1 just leaves me 1, so 2/5 plus 2/3 is 6 plus 10 is 16/15. Real quick side note, when you're adding fractions, you can cross multiply in an interesting way, right? I just did 3 times 2 plus 5 times 2. 6 plus 10 is 16 over 5 times 3, 15. And you're all like, thanks for telling me how to do fractions. Yeah?
Is that plus 2/3 U to the?
Oh yeah, 3/2, I'm sorry. Yeah. Alright, I like it. Everybody cool so far? Okay. Here, you go over here. Real quick, what is the cosecant of 5 pi over 6? It's of course related to the sine. 5 pi over 6 is in the what quadrant?
Second.
Second quadrant, so sine's going to be
Positive.
positive, because sine likes y, cosine likes x. SOHCAHTOA sucks, SOHCAHTOA is dumb. I'm really sorry if it just offended you. If you love SOHCAHTOA, great. Hold on to it. It doesn't do shit for you. Sine likes y, cosine likes x. If anybody ever took physics, vectors, if you think like that, easy as shit. SOHCAHTOA does nothing for you. All right, I'll stop myself. You get nice little jokes. Camp SOHCAHTOA, great. Sine is positive. It's going to be 1 over what sine would be, 30 degrees. Sine likes y, so it doesn't like it when it's far away from y, so it's going to be tiny. So it's 1/2. 1 over 1/2 is 2. Okay, so everybody with that?
Yes.
Okay. 2. How do I do this weird shit here? This weird thing. Yes.
Draw the triangle.
Yeah. So inverse trig. The input for a trig is an angle, so the output for an inverse trig is an angle. And I can, when you draw the triangle related to the inverse trig statement, it might not be a physically possible triangle, and we don't care. Because math does not always have to be physically possible, right? In this case, everything's fine. It's 5 over 13. That triangle will exist. It's all good. What triangle does this define? The angle tells me the triangle must have what?
Hypotenuse of 13
Yeah, the hypotenuse is 13.
and a short leg on the opposite side of the angle of 5.
The y piece is 5. Kick ass. And to figure out the tangent, I got to figure out the
Opposite of this.
Gotta figure out. No.
Cosine.
I love it. You guys are all like, I don't care if you don't like that shit.
No, no.
I'm gonna say it. All right. What are you gonna do? All right. Nothing. I don't care. Real quick, you guys know the 5 something 13 triangle? Yes. 5 what 13? 12. So I don't have to do Pythagorean, right? Old Greek dude that stole all this work from his followers. So tangent would be what? 5 over
12.
12. Yeah. All right. Okay. Okay. By the way, I really apologize if any of this stuff is like, too long ago or whatever. You really have to be pretty good with this stuff. So just see me if you need some help or whatever. But otherwise, just let it kind of come back. And of course, part C, the only reason I put part C down there is because I don't care what level I teach. I always get somebody tell me that the square root of x squared minus 9 is x minus 3 or something like that. It's like, then problems, that was easy, Jeff. Well, yeah, because you did that shit. Why can't I do this? Why is that not 2x minus 4? So much wrong with that. You would think maybe complex numbers should come in because it's negative 16, but even that's nowhere near the major issue.
When you factor anything x squared minus a constant, when you factor it, there's some stuff plus times some stuff with a minus.
And the really major issue is square roots are based on multiplication, correct? Because square roots, by the way, other side note. Okay, Jeff hates SOHCAHTOA. Jeff also hates that we have square root symbols. Those are one of the dumbest inventions ever. We have fractional powers. They are much more direct. We did not need square root symbols. Can a power distribute across a minus?
No.
A minus b squared, is that a squared minus b squared?
No.
No, of course not. Why not? Because powers are based on multiplication, not subtraction. So, of course you can't distribute the square root to both parts, right? What's the most you can do with this? Yeah, factor of 4. Square root of 4 is 2, and you're left with x squared minus 4.
Oh.
Is that cool? It'd be square root of 4 times square root of x minus 4. So do the part you can, leave the part you can't. Okay, okay. I like it.
So that's the answer.
Yes.
Oh,
Yes. I know, it's like, I just wanted to put that down there because I do want you to feel a little uncomfortable. You're supposed to know when the problem kind of stops itself. It's not an equation, it's just a simplification. That's all I can do, right? If it was 4x squared minus 17, I couldn't do anything. So I just have circled it. I'm done, Jeff. Right? Okay. So any questions from that sheet? We did part of it last time, part of it this time. Okay, all right. Okay. So, today, we're going to actually get into, the whole name of the freaking class. We're gonna get into some diffy-Q. What I kind of want to start with, I already said this, so let's put this up here. What's really hilarious to me is, who the hell's that tall? Why? Just mocking me. Okay. All right. This is, one of the most basic examples of a differential equation. All a differential equation is a relationship between x, y, y prime, y double prime, as high as you want. Right? Sort of like, what's a polynomial equation? It's a relationship between x to the 0, x to the first, x to the second, as high as you want, with constants thrown in there, yes? So differential equation is x, y, y prime, y double prime, blah, 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 blah. It's a function of those things. So this is the most basic, and of course I could write it in this format. Okay, I like it. And of course, how would you solve this equation? So the funny thing is, if I leave it like this, I can actually consider just doing this. Is that cool? And then I can integrate, and then I get, okay. So you've done differential equations before. Just very basic ones, right? So we didn't even call it differential equations. So what about this? Let me do one little change, very small change. What does that say? Can you interpret that in English?
Derivatives equal to itself, or
Yeah, the derivative of a function is equal to itself. Now you guys all know the answer.
E to the x.
Say again?
E to the x.
E to the x, right? That is definitely the function who's its own derivative. How would you actually calculate it though, instead of just go, oh, I know that. How do you actually, let's actually make sure that is the only answer. How would you do that? Why was this one easy? Easier. Why would I multiply that up there? Why would I do that first? What did I get together?
X's.
All my x shit, right? Okay, what would you do over here? You do the same thing. So what do you want to get? I want to get all my x shit on one side, all my y stuff on the other side, yeah? So what would the first thing you do be? Yeah, kind of like, right? Really cool little thing about algebra, 10 divided by 5 is 2, 10 divided by 2 is 5. These can just switch, right? That's awesome. So these just go dy over y equals dx, and then it can integrate, yes?
Mm-hmm.
All right, what's the integral of 1 over y?
Natural log of y.
Natural log of
Y.
Absolute value.
absolute value of y.
1. X.
Well, integral of 1 dx is x, right? Plus c. All right, let me stop for a minute. You guys sort of with me? By the way, we're going to do a deeper dive into these things. But let me just go ahead and tell you what the name of this kind of differential equation is. Didn't we just separate the y stuff and the x stuff? So math people, being the creative geniuses we are, we said, let's call that separable. Because you can separate the y and x. You guys kind of with me? So that's the name of that kind of differential equation, is a separable. Separable differential equations kick ass, right? They don't add anything new on top of the stuff we've already learned from calculus. Once I separate it, then the worst it could be is some weird, like, by parts or trig sub or whatever the shit you have to deal with once you get them separated, but there's nothing new to them, really, which on that level is kind of like, well, let's do that. Keep going here.
Solve for y.
Yeah, how do I do that?
take E to that.
E to that, I like that. By the way, what can I do with this?
You get the E to X times B to C, right?
Just another
Sure,
constant.
yeah.
Which would just be like constant, right?
Yes. Let's call this C1. So then I can call this C. You're going to see a lot of C1, C2, C3, especially later this semester. You are not used to being more careful with your C's yet. So later it's going to be a C1, there's going to be a C2. You've already done stuff like integrate something twice, so you have a plus CX and then you have to have a plus D on the next step when you introduce a new constant, right? But this is like a level above that, so that's in our future. So there we go. Isn't this basically what we... And the funny thing about this is, the absolute value of y, like, for example, if the absolute value of y is 1, what's y?
1 or negative 1.
1 or negative 1, right? Depending on what the sign of y is. So this would be y equals plus or minus, and the c can just kind of suck that in. Because the c could be positive or negative, so then it depends on, what would it depend on then? The value of c. I'd have to do what so we can figure out what c is? What would I have to tell you so you can figure out what c is?
X and y.
A point that the function's supposed to go through, right? Okay, I like it. Let that sit for a minute. So that verified what we already know. We know that the derivative of an exponential is itself. This actually proves that that's the only function. We started with a very general thing. What function is its own derivative? So now we've proven that, yes, that's the only one, an exponential function. I like it. Okay. Yeah, let me see. What do I want to throw at you? Not too many weird things. So let's go to some definitions. Start with something about, we are gonna be mostly concerned about ordinary differential equations. That doesn't mean we're never gonna look at something that really looks abnormal, but ordinary in this case only makes sense if I contrast it with what not ordinary means. And this is why I asked who's taking Calc 3 or not, because some of you guys have not taken Calc 3. There is an idea that is going to show up a few times this semester that I'm going to talk about right now. And this is known as partial derivatives. Right? So it's just one of those things that happens in math class. So like I had to take a painting class when I went to college to get, for my general ed, right? So I took a painting class. There are people in there that have been painting since basically the doctor hit him on the ass and they started painting, right? And here's Jeff like, it's a brush, okay. So they have this backlog. Okay, so what I'm saying is some people in here have come in with more than others. You did not have to take Calc 3 to take this class, correct? Some of you guys did not take Calc 3. But if you took Calc 3, you're going to be a little ahead. Oh well, big deal, who cares, right? Yeah, maybe I forgot this. If you think about it, remind me. I need to hire a camera person. Okay. With all that said, ordinary differential equations are ones that don't involve partial derivatives. So very quickly, what is a partial derivative? So if I have, for example, a function of two variables. In fact, let me even do this. Let's call this f of xy. So we'll just call it f. What's up? Sorry. Oh, square. Thank you. And I want to know. So this is. I love Calc 3. It's been too long since I taught it, but it's the whole idea of like the xy plane are inputs, and your outputs are like this canopy sitting over the xy plane. It just kicks so much ass, the ideas. But if you haven't taken Calc 3, you're okay. All a partial is, if I want to do, so here's what the symbol looks like. A regular derivative would look like that. It's called a total derivative. Partial derivative, we just went, let's just do this weird shit. It's got the little nifty, it looks more like a delta, right? Not a delta like this, but a delta like that. And all this means, what does this mean? Who knows this from Calc 3? What does that mean?
Keep one variable.
Yeah, which variable am I keeping constant?
Y.
Y, 11. So what's this function do if I change x but not y, right? So whenever I go to take the derivative then, my y's are constants. So what's the derivative of constant times x? Constant. And this would be a constant, so its derivative is 0, 11. So there's a lot more to partial derivatives, but to get through this class, that is all you need to understand. Who remembers what's another way to use, what's another symbol for this? So I don't have to write so much shit. F
Sub x.
sub x. So if I want to do the partial of f with respect to y, now I'm holding what constant? The x. So now it's constant times y. Derivative would be
X.
the constant. And of course, this is just a pure function of y, so that's nice. So that derivative is
2y.
2y. I love it. Let me stop for a minute. So even if you've never seen partial derivatives before, does it make some sense? You are just holding one of the inputs constant. That's all it is, right? And how you know which input to hold constant? Well, the one that you're not letting vary. This says as x varies, so obviously y is not varying. Okay. And of course, this symbol would be f and y. Help me out, guys. What is this then? It's like a second partial. So it's just take what we just got, but now take the derivative partial with respect to y. And what do you get? 1. Okay. What would this be? Same idea. Take what we just got, now hold y constant, take the derivative with respect to x. What do you get? 1. These are the same. That's going to be huge later.
They're always the same?
They are not always the same. But the really funny thing is, the only kind of functions that they're not the same for are stupid, freaky functions, right? Basically, piecewise functions, which I personally don't consider a single function anyway. But most of the examples you ever see are piecewise functions. And piecewise functions are almost always the answer about, well, what function violates this theorem? Piecewise, right? Okay, maybe. I just want to lay some groundwork with what partials are, especially if you understand a little bit about partials are, that's what we mean by ordinary. Ordinary differential equations, no partial derivatives, right? Partial differential equations would be an entire different class. Okay. Partials are going to be a tool we use later. We're not going to look at partial differential equations. So here, we do this. So here's some examples of ordinary differential equations. There's an ordinary differential equation. Incredible, Jeff. Neato. Let me ask you a couple questions. Let me see. Do you remember for polynomials what the degree of a polynomial was? So, for example, x cubed plus 4x squared minus 3. X cubed plus 4x squared minus 3. What's the degree of that? Third degree. It's just the highest degree I see. When I talk about the order of a differential equation, what kind of rules the day in a differential equation? The what's? The derivatives. So the order is sort of related to the degree of a polynomial. What does your gut tell you the order of this differential equation is? Second order. Because the highest derivative I see is a second derivative. Okay, cool. So there's a lot of nice analogies between differential equations and like polynomial equations. Okay. Second order. What would it take for a function to be linear? Can somebody give me a linear function? Just a linear function. I'll start. Here's a linear function. That's linear. Amazing, Jeff. Of course, what's the fundamental idea of making something a linear function? Every variable involved in the equation has a first, at most a power of 1. Yes. So what about x plus y plus z equals 7? Is that linear?
Yes.
Yes. What is that the equation of?
A plane?
Plane, kick ass. Right. All that matters is, so linear does not mean makes a line. Do you understand what I mean? Because that makes a plane, which is a series of lines, right? But the plane is not curved. That's the idea. Is that cool? Okay. So what about this? Order has to do with the highest derivative we're doing. Linear is not that. So what are the variables involved in this equation, by the way? There's an x. There could be a y. I didn't actually put a y in there. Do you see that? But I could have put a y here or whatever. Could be y. There's another variable. Y prime, y double prime. Those are the variables. You guys with me? So in the equation x cubed plus 4x squared minus 7, the variable is x. It's not linear because there's an x that has a higher power than 1. Here, those are the variables. Is this linear?
No.
Let me write it a different way. How can I rewrite this in a different way?
Y double prime.
Y double prime. Is that squared?
Yeah.
Is y double prime being squared? Does it look like this? Nope. Okay. So that variable is to the first power. Do you see that? It's being derived twice, but it's not being squared also, right? So there's a difference between order and whether or not it's linear. So that variable's fine. What about this variable? It's not being squared or cubed or whatever, right? Square rooted or whatever. Minus 2x equals 7. So that is linear. Kick ass. I love it. What about, I keep doing this to myself. So obviously if I do something like this, so here's where things get really weird. Yeah, okay, that really is weird. We could do that, but let's not do that yet. So obviously that already is it linear? No, so it doesn't matter what it's like. Right? How about this though? How about dy dx minus d squared y dx squared equals 4 over y squared?
No.
Not linear because
Power.
y squared. Okay. Yeah. So you can have a linear ordinary differential equation. You can have a nonlinear partial differential equation. These are all just words we use. Now, I am never as concerned with the word as I am with do you know how to work with it. But the classification tells us what we can do, right? Or the classification tells us what method to use. And that's going to be basically this whole class. One reason it's really kick-ass is because I got a whole bunch of people that have gone through Calc 2 at least. That kicks so much ass, right? You guys have survived that. I can start bringing stuff up, and some of us might need a little rust shaken off, but great. The other great thing about this class is, has anyone taken linear algebra yet? All right, let me see if you guys agree with this assessment. Linear algebra is, differential equations is, boom, 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 boom. You don't know that yet. It's very recipe-ish. Not the whole damn thing. There's going to be a little wow. And what I mean by that is, if you've taken linear, I think you know what I mean. Linear is like 50 some odd theorems and proofs and all this amorphous business. And one part of my brain loves linear and the other part of my brain loves difficult. They're very different. Differential equations is, oh, if I see this and this and this in that equation, I do this method, ba 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 ba. I see this and this, I do this method, ba 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 ba, right? Very kind of recipe-ish, right? And it just depends on what kind of student you are as to which one you like better, right? What was your point with that? I forgot. Okay. I always have to write little notes for myself because I'll just kind of go off and I'll forget where the hell I am. Blah, blah, we did that. Oh, no, we don't have to do that. Yeah, let's do this. Yeah, okay. So I can't remember if I asked this last time. So you've got this notation here. You've got this notation here. And then you've got notation that looks like this, for example, right? Does anyone know the first notation, who came up with that?
Was that Newton?
Yeah, this is Leibniz. This one, that one's got an interesting history. The prime notation. Does anyone know? Again, it doesn't matter if you know or don't know who the hell came up with it. But do you guys know it all? Newton is this one. Newton did a lot of stuff. Obviously, the most famous thing Newton's known for is the acceleration of gravity, correct? So he did a lot with kinematic formulas. When I say kinematic, do you guys know what I mean? Kinematic, the study of motion, so like those are the basic formulas of physics. So his notation was almost always about derivative with respect to time. So he put a little dot for dx dt, a little double dot would be d squared x dt. And the really, really funny thing is, if I wanted the fourth derivative, he would do 4 with a little dot. So that, we're like, good try, dude. Sorry. This was Lagrange, but the funny thing is he stole it from Euler. The history of math has got a lot of like subterfuge. It's very, you actually could make an interesting little mini-series out of some of the stuff that's happened. I think I told you guys about Cardano a little bit. Yeah, so there's a lot of, they would have math duels. I think somebody was telling me they had read about that. They would come with like these prepared math problems, kind of throw them at each other and do stuff. Almost kind of like, what do you call it, rap battle, just slightly less cool. Although some rap battles are not that cool. So I just want to throw that at you. It's never important. I do like pointing out the history of some of what we do. The most important thing for us is just being able to work the problems, right? But it is good to know where this stuff came from. And it's also interesting to know that there were people that stole shit from other people. There's all this crazy stuff. Okay. Blah, 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 blah. Yeah. Okay. We already talked about that. Oh, okay, cool. All right, let's do this. Actually, let me do this. I'm gonna intersperse our definitions with some stuff to kind of think about, because I don't want to just barf up definitions to you. We're all going to go slightly insane. What do you guys think about this? Let's do this. Yeah. You can do it, John. Yeah. Actually, let me make this. Yeah, let's do this.
Something whose second derivative is itself negative.
Sure, but it's got to be, so the second derivative has to be the opposite of what it was to begin with, right? So whenever you're given a differential equation, sometimes you can just read it more in English. What function is, its second derivative is the opposite of what it was in the first place? So again? Sine and cosine? Yeah, so like, let's say that y is sine. What would y prime be?
Cosine.
No, cosine, right? Remember this, I don't know, has anybody ever, some of you guys had me. Do you remember what I said about cosine? Anybody? Yeah, cosine's an asshole, right? Real quick, for example, do you guys remember what sine of 2 theta is, identity-wise? 2 sine theta cosine theta. Is it anything else? That's what it is, correct? Let me say this again. Sine of 2 theta is 2 sine theta cosine theta. Does that sound familiar? What is cosine of 2 theta? Cosine squared theta minus sine squared theta, or
1 minus 2.
sine squared, 1 minus 2 sine squared, or 2 cosine squared minus 1? I don't know, against some. So the funny thing I noticed a while back was thinking cosine is an asshole actually is awesome. Let me throw another one at you. Sine of A plus B. Who remembers that identity? Sine A cosine B plus sine B cosine A, right? So what does sine do? Sine says, oh, there's a plus, it's still a plus. Hey, cosine takes turns. Sine A, and then you do B, and then I'll do B, you do A. See, sine's nice. What does cosine of A plus B do? Cosine A, cosine B, me first, screw you. Oh, you got a plus? I'm going to make it a minus. Sine A, sine B. So, again, believe it or not, that is not technically true. Cosine does not have the ability to be an asshole. But it's a really, as far as I know, it's a really kind of cool way, for me anyway, to memorize these things. And you do happen to have these identities memorized. Okay. Did I show you the handout I have up? The trig laws? The green piece of paper? All right. Did I show it to you? There's a black line in the middle. You have to know everything above that black line. Everything below it, you don't. The reason is I have everything memorized above the black line. I don't have the stuff below the black line. I'm never going to make you memorize more than I do. right? It's sort of like the PE teacher that makes you do stuff that he could never do. And I'm like, I need to be able to do it too. Okay. Back to this. What is y double prime?
Negative sign.
Yes. So that very much is an answer to this. What could I add on top? Why is it just one answer? Because cosine also works, correct? So what if I had y equal cosine x, y prime equals negative sine x, and then y double prime would be negative cosine x. That also works. Still not enough. Be more general. What about 2 sine x?
Sine or cosine plus or minus.
What about 2 sine x?
C.
What about 7 cosine x? All right, so watch. You ready? You ready? So I need to have a sine and a cosine, but this can have any constant at once, and this can have any constant at once. That entire thing solves this. Does that make sense? If separately they work, and derivatives are linear functions, what the shit does that mean, Jeff? Why is a derivative a linear function? What is the derivative of x squared plus 4x? What's the derivative of x squared plus 4x?
2x plus 4.
Didn't you just distribute the derivative, sort of? You didn't really. But linear functions are the ones that operate as if you distributed them, right? So if this works for this and it works for this, it works for the combination of the two. Something we call the superposition of those two. Are you guys still with me? You guys kind of, okay. Oh shit, I'm sorry, I've lost it. The nice thing is we're going to do a deeper dive later over everything I'm talking about in terms of problems, right? There will be a whole time we discuss this idea of superposition of multiple things that work. Okay. How would you check that? Just throw it out, right? Okay, maybe. Let's see, real quick. What's y prime? C1 cosine x?
Minus.
Yeah, minus C2 sine. And then what's y double prime? Negative C1 sine x minus C2 cosine x, yes? Isn't that the negative of this? Okay, cool. So if you have multiple functions that solve a differential equation, you just add them with constant coefficients, and that's the general answer for that. Okay, maybe.
Yeah.
Okay. So back to definitions for a bit. Let's see. Where did I leave off? Darn it. Blah, 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 blah. Oh, yeah, that's right. Okay. So let's say I have a... Let me see. Let me ask you this. Let me see what you guys do. Can you give me a linear first order ordinary differential equation? Write it down. Not those words. Give me an example of a linear first order ordinary differential equation. It's basically every freaking definition word we've talked about. Linear first order ordinary differential equation. I want to keep an eye on the time because I want to take us on a little field trip. Our class is over at 10:50, is that right? Yes. Okay, thank you. You guys could have said anything right there. It's over right now, Jeff. We're actually overtime. What do you guys, somebody want to give me what they've written? Anybody wrote anything?
4 times dy over
Wait, sorry, go ahead.
Yes, sir. 4 times dy over dx is equal to 5.
4y, it's 4 dy dx
4 dy over dx is equal to 5.
equals 5. Kick ass. That works. Anybody else write something more? Yes?
I
did, dydx plus 74 is equal to negative 5.
dydx plus
74
74
is equal to negative 5.
is equal to negative 5. Okay. I'm gonna make one little change because you could just put these together, right? Let me just do that. Okay. You know, like whatever, Jeff. Okay. She didn't say that. I said. Okay. All right. Yes.
Sorry. 3 dy dx equals 3x plus y.
Yes. Okay. So every possible answer must look like this, or must be able to be written like this. Get in there. Oh, yeah. You can do it, Jeff. There you go, buddy. I feel like I left something out. Did I leave something out? Does that match everybody's, what they gave me so far? Oh, this is so weird. Okay. Why do I feel like they forgot something? I don't think I did. Okay. Alright. Blah, 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 blah. So what's really cool is I could actually rewrite this thing. Let's say that this is 0. So then I got a0x dy dx plus a1xy equals 0. Obviously, for example, this problem, what was a1 of x? This example, what was a1 of x? 0. Kick ass, right? So those constants, even though they're functions of x, 0 is a function of 0x. There you go, that's a function of x. If I divide by a0, and well, let's do this. If I multiply by dx, we can see, let's see this. Later this semester, here's what we're going to do. We're going to call this m of xy dy plus n of xy dx. So this is a general first order linear ordinary differential equation. We're going to rewrite the damn thing in so many different ways. There's another way to rewrite this. This was what I was about to do. If I divide by a0, I'll get dy dx plus p of xy equals 0. Right? So again, part of this is if I want to know what the slope and the y-intercept are for a line, I can be given it in so many different orders, but I want to put it in a certain format so that that pops out at me. You with me? So y equals 3x minus 7, I can see the slope is 3. What about circles? So what if I wanted to know the center and the radius of a circle? And I give it to you like this, x squared minus 4x plus y squared minus 5y equals 11. Can I see the center and the radius the way it is? No, I have to complete the square and put it into the general form of a circle. Cool. So certain methods we use to solve differential equations requires me to put it into certain formats. So part of the course is just going to be putting it in certain formats based on certain things you notice about the way the equation is written in the first place. Okay. What? True. Hey, we already talked about that. Crazy. Cool. Okay. Yeah. Okay. Coming back to something we did earlier. I want to give you a couple more examples of something that's not linear. Let me ask you this actually. Let's see, is there a good counterexample? All right, there's not really a good example. Can anyone tell me why this would be considered not linear?
because it's y dy dx?
Yes. So in just a straight up normal equation from like algebra, x squared is not linear because it's x times x, right? It's what is a function of multiplied by itself, so it's not linear. It's got a power other than one. This is kind of weird. These are both dependent variables, right? Y is dependent on x. Therefore, dy dx is also dependent on x. They're both dependent variables. So if I have y times dy dx, that is not linear. It's not as obviously not linear as x times x is x squared. That's not linear because I can see the power of 2. This one, I can't even combine them because one's got a derivative, the other one doesn't, but it's still a product of two things involving the dependent variable. That is not linear. Yes?
Is it because, like, if X were to change, they would change too fast? Like, they would both change since they're both the same?
No. Not necessarily, no. Yeah, I like that idea, but not quite. Because if I throw an x there, then it's not going to be that big of a deal. And real quick, if I divide by y, then it's a little easier to see this is a problem. So now it's obviously not linear because what's the power on y? Negative 1. Kick ass. Okay. All right, I like it. I like it. Okay. Yeah. Oh, and and of course something like this is very obviously not linear. Yes? So it's not just not linear if something is to a second or third degree, third power. It's also not linear if it's inside of another function. So if I had y double prime minus tangent y, y double prime minus natural log of y, it's not linear. Those are not linear functions. Okay. Blah 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 blah. Oh, okay. So I always have to keep an outline to keep myself straight. When you solve a differential equation, we've already talked about this a little bit, you don't get a specific answer, correct? Every time you've integrated an indefinite interval, you always get, does somebody know what it's called? You don't get a solution, you get a something of solutions. Don't go against you get a family of solutions, right? So in DE, in differential equations, we actually, when we solve a differential equation, the answer is a function, right? In fact, it'll be a family of functions. So for example, if I have, let's go back to something we did earlier. We did this. What was the solution we got?
E to the x.
That was c e to the
X.
x. I love it. Right? So obviously this is a family of solutions. If I wanted to know an exact solution, I'd have to give you a point that the function goes through. I could have functions, let me see if I can come up with an example. Did past Jeff give me an example? Sort of. Blah, 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 blah. Yeah, sure, okay, that'll work. What about this here? What's the solution? Yeah, the neat thing, let's do this. There's kind of something interesting about this. So dy equals 1 over x dx. So you integrate that, you get y equal natural log of x plus c. Real quick, let me see. Let me write this a different way. Okay. I could put plus c there. We'd all be happy people. So what the hell, Jeff? But I want to show you something kind of cool. Let me write it like this instead. Okay, so what does that do for me? What do I do when I have natural log plus natural log? Say again. Yes, multiply the insides. And why is that? Because of course, what's a log? What's a log physically? It's this thing turtles sit on. No, I mean the answer to log is a power. And of course, when do I add powers? When I multiply the things that we're working with, right? So that's just kind of a way to remember this rule. So all the properties of logarithms are the same as the properties of powers, because logs are powers. Now what's wrong with, something that's kind of wrong with this, when we think about a differential equation, is I need not just a single answer, I need an interval of solution. Now, I want to help you not freak yourselves out. This has nothing to do necessarily with the interval of convergence, for example, just in case that sort of like cropped up in your head. What was interval of convergence all about? Where'd that come from? Series. I love it, right? This is not that. The interval of solution would mean, tell me what the domain of this is. No, it can be negative, can't it?
Yeah.
Because it's an absolute value.
Just not zero.
Basically can't be zero, right? So the domain is negative infinity to 0, 0 to infinity. So when you solve a differential equation, the second thing to consider is, on what interval does this exist? It can only exist on one of those intervals. We can't pick which one yet, because I don't have enough information for that. So what if I do this? What if I tell you that this goes through the point, what do you got, Jeff? Sure. Let's say, it doesn't matter, Jeff. 2, 1. You can already tell me which interval this thing works for, right? Which interval would it be?
0.
So the interval on which this solution exists is from 0 to infinity, because 2 is on that interval. Could you figure out, of course, what the C is?
Yeah, you have.
Yeah. You just plug 2 in for x, and then you solve, you let it output be 1. Okay, I like it. So when you solve differential equations, not only do you have to get the functional answer, but you also have to identify the interval on which it could exist. So if I did not give you an initial condition, you would have to identify it could be either one of these. Now it kind of depends on if the question kind of asks for it, but it's always in the background. Okay. All right, we already did that. Oh, okay. Let me ask you this. All right. So I told you I was going to sprinkle in between definitions. Let's look at something a little more concrete. Can you very quickly tell me if this solves this? Yeah. Can you tell me if that function is a solution of that differential equation?
Yeah.
Yes, okay. So y prime is 2e to the 2x, y double prime is 4e to the 2x, right? So if you do 4e to the 2x minus 2e to the 2x minus 2e to the 2x, you do get 0. So that is a solution. I want you to notice something. if you look at the way this is set up, do you see how this sort of looks like this form in a way? Okay. I didn't just do something to get there. I just noticed, if I sort of pretend like derivatives are powers for a second, it kind of looks like that. Yes? Okay, go with me for a minute. How do you factor this?
And minus 2 plus 1.
And if it equals 0, you would get m equals
2
2.
and negative
M
1.
equals negative 1. Do you see how the 2? So what do you think another solution might be? E to the
4x. No, negative 1x.
negative x.
That's
Right?
4.
No worries, no worries. The way I write, you never know. Now, really quick, I want to show you this right now. And again, everything I'm showing you, we're going to do a deeper dive in later. It makes no sense on the surface to say, well, yeah, that kind of looks like that, and that does that, so yeah. So I could ask you to verify, and it works. E to the negative x is a solution. So then you ask yourself, well, does that kind of shit work all the time? Right? So one thing we're going to do this semester for certain problems, and let me say this. Let me say a phrase here, see how you guys react. Partial fraction decomposition. Yes? Everybody should know it, especially from count 2.
Yeah.
Isn't partial fraction decomposition, aren't you kind of assuming what the answer looks like? Do you know what I mean? Don't you start with, you factor the bottom and say it equals a over x plus 1. You're assuming that the answer looks like that, and then you're solving for the parameters, not the variables. A, B, C are kind of like another step above variables, the parameters. Are you guys with me? It's up there. In some differential equations, we can just guess what the answer looks like. What time is it? Oh, shit. What time did I say we have?
10:50.
All right, this is the last thing we'll do, and then we'll head out for a really quick tour. A function that directly relates to its own derivative is an exponential. So on one level, it makes sense that a possible answer for this would be e to some constant times x. Because its derivatives would be like terms with its other derivatives, and then it could possibly come together and make 0. Yes, just like you saw over here. If I assume the answer is this, what's y prime? And what's y double prime? And then if I plug that shit in, I get m squared e to the mx plus, minus m e to the mx minus twice e to the mx equals 0. E to the mx, can that ever equal 0? Can e to the mx ever equal 0? There is a what at 0 for e?
Horizontal.
There's an asymptote. It can never equal 0. I can just divide by that shit. Don't I actually get m squared minus m minus 2? Do you see that? So we will not always be able to assume what the answer's form is. But we will actually be able to do it a decent amount of the time. It's kind of cool. We just go, I think the answer should look like this. And they just assume it does, and you plug that shit in. This helps me figure out what m's actually make it work. Not every m will make it work, of course, right? Okay, I like it. I like it a lot. All right, guys. I always suck with the definition chapter, so I'm sorry if I was like all over the place. It's important to understand linearity. It's important to understand ordinary versus partial and so forth. When we hit partial derivative stuff, I will kind of review it a little bit more. You do not have to know everything about partial derivatives. We're just going to use it in a few different places. So do this for me. Pack up. It's going to take me a minute to get myself together. Kind of walk out the door and go in the direction of the stairs, but go really slowly so I can catch up to you. Some of you guys work in the Math Science Center, so that's one place I'm going to. So you can talk to yourselves maybe about how it works.
Are you coming back in here after you?
No, we're not coming back.
Can I ask you a question real quick?
Yeah. So I just put it in the form so we can actually go together with the other elements.
That was on my notebook. This vehicle is not equipped with airbags.
This vehicle is equipped with. Alright, if you get that running on the road, I see you driving down the road on a notebook.